Good morning, sir. I am Prarabdh Purkar. This is my submission for assignment number 3 in NIC course, Floor Plan Optimization using NSGA tool. So our problem statement is we have to design a chemistry workspace containing of equipment room, laboratory room and a seating room. The dimensions of this chemistry workspace are given and we have certain restrictions on laboratory room. So what we have to do is our task is to minimize the cost of whole construction of this whole area, and we have to minimize the when we have to maximize the area of this laboratory. So we have conflicting objectives. Uh, One thing to note here is for our algorithm in coding, we will be not, instead of doing maximize problem, we will make the problem both minimize and minimize. How will we do that? Instead of saying we are maximizing this laboratory area, we will say we are minimizing the sitting space plus equipment room. Just we have to change the function, and at last, while showing the Pareto front, we will be again showing the main maximizing and minimizing objective functions. We will convert it back. So this is our objective function. So as you can see, this in this objective function, we are minimizing both the objectives. The area left, that is 25 square minus width into length. Width is and length are of laboratory, and the cost according to the cost for each of the space of laboratory equipment and sitting area. These two are both are minimizing and conflicting objective functions. So this is giving the output. So then we will see our main function. Our main function, this is the reference for this code. This is little bit motivated from here, arps.com. So what we do is first we initialize our various parameters and generate the random population. Then we calculate fitness of each population candidate and do non-domination sorting. What non-domination sorting will basically do is it will give rank to all the solutions, rank from like 1 to 10 or 1 to whatever, according to non-domination sorting. Then we calculate crowding distance, and then we sort the whole population according to the rank and crowding distance. After sorting, we will generate new offsprings by crossover and then by mutation, and then we merge those new offsprings into the old population by again sorting according to non-domination sorting algorithm and crowding distance. We will keep repeating these above steps for a certain number of generations. Then at last we will plot the Pareto front. So here we are initializing some hyperparameters like population size, the maximum number of generation, that will be the maximum number of iterations we will be looping through, and this is the crossover probability. For 100 population size, the number of crossover offsprings will be 60. Then we will have a mutation probability again, and for 100 population size we have 40 mutants. So after the crossover and mutation, we will have 100 plus 60 plus 40, that is 200 population size, and then again we will take 100 only, first best 100 population with best fitness. So first we will define an object with certain attributes like dot width, dot length, dot cost, dot rank, dot domination set, dot domination count, dot crowding distance. So we will find the cost according to the our objective function as we have seen earlier, and we will give rank according to this non-domination sorting algorithm, and with the domination set and domination count that I will be explaining later, that will help us in sorting after non-domination sorting and crowding distance sort pop. So then we will do crossover and mutation. So here we initialize the population with all these attributes, say for this population size 100. So see, as you can see, we have been given range for width of 10 to 15, and for length we have been given a limit for 10 to 18. So we are generating a uniform random number between these. So and we find the cost according to this objective function. So after this, then we do non-domination sorting. The basic idea is, if we are given two or more solutions, say two, I and j, then solution I is preferred over solution j if the rank are different, then the lower rank is preferred, and if the rank is same, then we will see the crowding distance. Which population has more crowding distance, that will be preferred more. So the rank one the solutions which get the rank one will be considered in Pareto front one. They have the best fitness. Solutions of same rank has same fitness, and lower rank is preferred over others. That is clear. Then comes the concept of crowding distance. As you can see, crowding distance, uh, see if we have two or more solutions of the same rank, then again we have to sort. That's why we do crowding distance. That's why we imply this crowding distance. The one located in the less crowded region of the Pareto front is preferred. This is done to ensure population diversity. Basically, what we are seeing is, we are finding the points which in which a cuboid will fit the best. A larger cuboid will fit the best. Let's go inside non-domination sorting to gain some more intuition. So here is the code. So again, population size we take, and what we do is initialize the domination set and domination count to empty sets and 0. So what they are, so to give rank to all the solution, we see if a solution has any other solution with both the values less than or equal to value of that solution. If we don't find any values lesser than that solution, then we give it rank 1. Otherwise, we don't assign any rank to that solution at that time. Iteratively, we do this for further ranks like 2, 3, 4. After one, after giving all of them rank 1, iteratively we do this, and if all the solutions are ranked, then we break this loop. So what we are doing here is, we are giving rank to each solutions according to a condition. Here is the condition. Suppose if A is located at x1, y1 and B is located at x2, y2, then we say A dominates B when x1 is less than equal to x2 and y1 is less than equal to y2, and x1 is less than x2 or y1 is less than y2. This is to gain more intuition about it. We can simply say, if we find more both the lesser solutions with lesser values then that solution, we assign it rank 1 basically. Then we go to the crowding distance. What the crowding distance does is, it finds the it finds the distance, and what we do here is, we find the maximum largest cuboid it can fit, which will have only two particles. Largest cuboid, which 2 points have largest cuboid, we will choose those. Less crowded is preferred, means larger the cuboid, that will be preferred. So basically, crowding distance should be more. How we do it is, we for each rank, inside each rank, we find all the cost. For rank 1, we find all the cost, and what then we do is, we sort it according to its cost. Then we give outer 2 points as infinity. Like here we have given minimum index to infinity, and here we have given last index to infinity. And in between all the points are the cuboid distance, crowding distance is calculated according to this formula. This is simple formula, and after this we will find all the crowding distance, and then comes the sort pop function, that is to sort according to both rank and crowding distance. See here, first we are sorted according to the crowding distance, and then we have sorted according to the rank, and then we have merged it through something. Then comes the crossover theory. This what we do is in crossover theory is we take two populations, two particles, and then what we do is converting them into the binary form. We can take any number of bits. Here I have taken 20, and what we do is we generate a random number in between the length of that binary number, and say suppose we say 1 to 20, then the random number is 7. So we will partition that binary number from 1 to 7, and then 8 to 20. We do that for another number x2. So then what we will do, we take first part of x1 and second part of x2 and merge them, and then we generate a new number. And then what we do again, we take first part of x2 and second part of x1, and then we generate another number. In this way we get y1 and y2. This is called crossover theory. And then comes the mutation theory. Mutation, in which what we do is we again convert the number into binary, and we generate two numbers in between them, and we just swap those two numbers like binary numbers, like some 7th place to and 13th place are interchanged. This is called mutation. So again we come back to the main function to show what were we doing. uh, First we initialized some parameter, and then we initialize the population also and find the cost. The cost is basically the fitness value. We find all the fitness value, and then first what we do is non-domination sorting, then find the crowding distance, and then again sort according to this non-domination sorting. Then comes the crossover theory. Main genetic algorithm loop. What we do is we find the we do crossover. Suppose for 100 population, the crossover probability is 0.6, so we generate 60 new offsprings. This here are, as you can see, what we were doing is interchanging first part and third part like that. So we are getting two new numbers from old two numbers. We have to take care of these ranges, like width should be 10 to 15 and length should be 10 to 18 to get this accurate. Otherwise we will get out of boundary points. We can get out of boundary points by changing the numbers also. And then we find the cost for those new points, and then that is called pop cross. And again then we do the mutation. Likewise I said, we will be interchanging or called swapping the two bits. And here we have also have to take care of this range of length and width, and then we find the objective function, and that is mutation. We call it pop mute. So after that what we will do, we vertically stack the population and crossover population and mutation. And after vertically stacking, what we do is again we do non-domination sorting. We do crowding distance, and then we do short pop function. And so in this way, as you can see, we do this in a loop for n number of iterations. The number of iterations we have taken are like 20 or something. uh, so for after doing that, for converting it back, like I said earlier, we are doing minimize function. We are converting back into maximize minimize objective functions by subtracting the old minimizing function by 625, that is 25 square. And here is a code for plotting the Pareto front. Now we will be running the code for 20 iterations and with population size of 100. Let's run the code, and we will see the Pareto front changing over the generations, over the 20 generations. See, as it was very much expected, we got this tick mark shaped parabola shaped view Pareto front of rank 1. So what it denotes it, this is X. X is area that we have to maximize laboratory, and second objective is cost, that is overall cost that we have to minimize. So to, as you can see, this is more towards maximize side, bend towards maximize side, and not bend towards minimize side. So this is our Pareto front, and by seeing this we can say the most optimal solution if we are looking for is around this 180 point and uh, 2.5 into 10 to the power 5 cost. So this is the Pareto front we are getting. So thank you.